Hello guys, this is David. In a previous lecture, we have learned how to do displacement analysis using vector method. In this lecture, we will continue with velocity analysis. First of all, let's talk about the goal of velocity analysis. The goal of velocity analysis is to determine the velocity of a particular point on a rigid body. And to do so, we need to derive the derivative of a vector with respect to time. To be honest, there's no magic about this at all. It is as simple as differentiate r cosine theta and r sine theta with respect to time. However, it is hard to tell the physical meaning of the result you got from the differentiation. Therefore, here I choose to express the vector using polar coordinates and again differentiate the vector with respect to time. From the result, it is clear that we will end up with a vector in normal direction and a vector in tangential direction. In the following slides, we will express these two terms as r dot and omega cross r for the sake of convenience. Notice that if the length of the vector doesn't change with respect to time, the r dot term will not appear. In contrast, if the angle of the vector doesn't change with respect to time, the omega cross r term won't appear. Okay, now let's work on the rocker crank example that we have mentioned in the last lecture, and recall the two constraint equations that we have derived using vector method. Since we have already obtained the vectors r1, r2, r3, and r4 to represent the displacement of each rigid body, now, in order to do velocity analysis, we differentiate them with respect to time to obtain v1, v2, v3, and v4, and what we will end up with are these two constraint equations. Notice that the reason why there's no r dot term in the equation is because the length of the vectors r1, r2, r3, and r4 doesn't change with respect to time. Now, with these equations, the system is again shown to be a single DOF system. Why? Because we have three unknown coordinates, θ1 dot, θ2 dot, θ3 dot, and two constraints. That makes it a single DOF system. You may have questions like, what about the coordinates θ1, θ2, and θ3? Aren't they unknown as well? This is a good question, and to answer this, just recall the fact that these coordinates have been already determined in displacement analysis. Therefore, in this case, they are known coordinates. Now, to solve for these three coordinates, θ1 dot, θ2 dot, θ3 dot, all you need to do is to specify the value of one of the coordinates, and the rest can be easily determined by solving the two equations with two unknowns using MATLAB. Once θ1 dot, θ2 dot, and θ3 dot have been determined, then the rest of the coordinates can be determined by the following relationships. The next example is a slider crank mechanism. Again, these two constraint equations are obtained from displacement analysis. Identical to the last example, in order to do velocity analysis, we differentiate the vectors r1, r2, and r3 with respect to time to obtain v1, v2, v3, and two constraint equations for velocity analysis. Notice that the reason why there's no omega 3 cross r3 is because the angle of r3 doesn't change with respect to time. With these two constraint equations, we again have obtained a single DOF system, which can be easily solved using MATLAB by the exact same procedure that we mentioned in the previous example. Once θ1 dot, θ2 dot, and x3 dot have been determined, the rest of the coordinates can be determined by the following relationships. And to notice that the reason why y3 dot and θ3 dot are 0 is because y3 and θ3 are 0 respectively. The last example that we will discuss about is inverted slider crank mechanism. Basically, the procedure is the same as the previous two examples. The only thing that should be mentioned is that both the length and angle of R2 change with respect to time. Therefore, the derivative of R2 is R2 dot plus omega 2 cross R2. After all the unknowns have been solved, the rest of the coordinates can be determined with the following relationships. And the reason why θ2 dot is equal to θ3 dot is because θ2 is equal to θ3. So this is how we do velocity analysis of four-rod linkage mechanisms using vector method. In the next lecture, we will continue with acceleration analysis. See you next time.